Okay, picking back up with the fundamental theorem of calculus, this first FTC, this accumulation of area, that's how much your y values are going to increase. Picking back up with this stuff. Before we actually get to this next example in the notes, I want to do something. If you're absent today and you're watching the videos, then we typically would have done a warm-up that kind of helps our brains get primed for this type of an activity. And I want to go through with you because I think sometimes students can relate better to the situation in the warm-up. That kind of helps them put this math more into a context where they can understand it. So let's go through it. It says today is blank. Well, today's the 2nd for me. I don't know what day it is when you're watching this, but we'll just say whatever. Today is blah. Suppose you have $100 in your bank account. So right now, today, right, if you think about, we're going to end up kind of graphing this situation. Today's date, you don't have to put a number, it doesn't matter, but today we have $100 in our bank account, right? We're going to be graphing this situation. Today is the blah. Suppose you have $100 in your bank account, then A. 2 days ago, you got paid $20. And then it asks, what was your bank account balance before you got paid? So we're trying to think about this. 2 days ago, you got paid, right? So my bank account went up. How much did it go up? 20. If it's at $100 right now, if I go back 2 days, I'm trying to figure out what was my bank account so that when it increased, when it went up by 20, I end at 100. Well, hey, that means 2 days ago, this bank account, it would have had $80 in it, right? Because 2 days ago, if you had 80 in your bank, then when you got paid, when it goes up to 20, you end with 100. And this one's weird, and students will sometimes have trouble connecting it. It's like, hey, you're getting paid 20, so your bank account should go up. Here, I was graphing, and I had the point at 100. Why does my graph go down? Why is that first point below? Or why is that second point below my first one? Well, it's because you're working your way backwards, right? You're taking 100, and what you're doing is you're subtracting the previous amount of change. You're trying to work your way backwards, right? If you had 100 and then you gained 20 from it, you would do 100 plus 20. That would get you forward into the future. But whenever you're trying to work your way backwards, we're trying to figure out how much did I have so that when it gained 20, I ended with my current, right? So basically, I would take my current and I would subtract the change, and then that's what gave me the previous amount. So it's weird. Even though I gained 20, graphically, that function goes down. Well, let's extend this idea. Part B. It says the day before we got paid, you lent a friend $10. Okay, so that's going to cause your bank account to lose $10, and you're thinking, how much was in your account prior to doing that? Before you lent your friend the money, how much did you have? Okay, well, remember, we have 80. 2 days ago, we have 80. If you lent your friend $10, I mean, kind of think, hey, this graph, lending your friend money, that's going to cause your bank account to go down, right? But no, we're trying to figure out how much did I have so that when I lent my friend $10, I ended with 80, right? So we're trying to think, how much did I have so that when I added in this negative $10, right? Because when we lend a friend, it counts as negative. I end with the 80. Well, basically, what you have to do is end up subtracting this negative over. And when you subtract the negative, it's going to end up adding that value, right? So if I had 90 the day before I got paid, right, I had 90. Let's recap. If I had 90 3 days ago, then I lent my friend the $10. Okay, so it went down. That makes sense. Then I got paid, so it went up 20. Like, it makes sense when we're working from the past forward, right? When we're working from the left to the right. But if we have to work our way backwards, we should still be able to get it. Let's go back through this part A. Remember, today we had $100, and then it says we got paid $20. And we're like, well, okay, we got paid $20. Why did your bank account go down? Because you're trying to think, what did you have so that when it went up, you end with 100. So even though getting paid causes your value to go up, when we're trying to graph that point that happened in the past, whenever we're trying to work our way backwards, even though this 20 is positive, right, causes my amount to go up, it actually causes the graph to go down because we're working our way backwards. Kind of the same thing. Lending your friend $10, that's you losing money. But graphically, what that's going to do, though, is that graph goes up because you're trying to figure out how much did you have before you lost or you lent the $10. So just be careful. Whenever you're working from your point of reference, whenever you're working from that point backwards, from that point, from the right to the left, everything is kind of reversed. When we end up gaining this money, right? We got paid 20, our amount should go up. Graphically, what happened to it? It went down, right? And it went down because we were trying to figure out how much did I have so that when I gained, it ended at 100. Or, hey, when I lose $10, it actually caused your graph to go up because you're trying to figure out how much did I have so that when I lost the $10, it ended with the 80. Everything's easy when we work from the left to the right, when we go from a point in time forward into the future. But whenever you're working in reverse, everything's just the opposite, right? You're trying to figure out how much did I have so that when I gain or when I lose, I end up with my desired result. It's a little bit tricky, but I think hopefully putting it in terms of money helps. The part C is a little bit easier. It says, okay, so tomorrow your mooch of a friend is going to ask for $5, and of course you're such a sap that you're going to agree. But at least your $50 paycheck will hit your account the following day. So how much money will be in your account after each transaction? Okay, so today, remember, we're back at our current point of reference. Today we got 100. Tomorrow we're going to lend our friend $10. That means my bank account's going to go down. Right, so tomorrow it's going to be at 95, and then the day after, so 2 days from today, well, I'm off the screen, that's totally my bad. Remember, today we were at 100, then we lent the friend another $5, so now it's down to 95, and then the day after, right, 2 days from today, you're going to get paid 50, and when you get paid, it's going to cause your amount to go up, and then you'd end up with this graph up at 145. Right, so that one was at 95. And then this one's over at 145. From your pivot point, or from this point of reference, from this point forward to the future, when you're working from left to right, everything kind of makes logical sense. When your bank account goes up, the graph goes up. When your bank account goes down, the graph goes down, right? When you lose money, the value goes down. When you gain money, the value goes up. But when you're working from your point of reference to the left, when you're working from right to left, everything's reversed. When you got paid, right, your bank account goes up. When I'm working my way backwards, the graph actually goes down because you're trying to figure out how much they have so that when it went up, I end with 100. Or when we lost $10, right, or when we gave away the $10, graphically, your function's going to go up because we're trying to work our way backwards and figure out how much did I have so that when I lost, when the graph goes down. Okay, so just be careful. Working from the right to the left, everything's just a little bit backwards because you're trying to figure out how much did I have so that when you gain or when you lose, you end up with a specific desired result. But working from your point of reference to the future, that's easy. Positive means up, negative means down. But whenever you're working from your reference point to the left, it's a little bit tricky because everything's backwards. All right, but let's try to connect this idea to this next example with calculus. Hopefully the bank account one makes sense. If you were here in person, it would probably make a little bit more sense. But alas, you hopefully just have to follow through, and hopefully it makes sense in the video, but I don't know. Okay, so let's think back, and let's do this next example. It says the graph of f prime is shown below, or it's shown on the right, and it says use this figure and the fact that f of 3 equals 5. So we have 1 point on the function. We know we have the point 3, 5. Lovely. Let's go graph it. So let's go 1, 2, 3, 4, 5. Let's do some negative 2, 3, 4, 5. So 3, 5. Here's my point of reference. It's like my pivot point, right? This is like my today example from the warm-up. So anything from this point to the right, from the left forward, that's going to be easy. When I gain value, it goes up. When I lose value, it goes down. But potentially working my way backwards is a little bit tricky. Right? If you want, you can think about these fundamental theorem of calculus as being like area bank questions. When I have this derivative and I have the area underneath it, here it says the area of this region is 4. It says the area of this region, but be careful, that region's beneath the x-axis. It says the area of that region's 9, and then the area of that third region is 2. So it's just telling me the size of each region is different, right? In the previous example, it gave us these geometric areas or these geometric regions. So we had to find the areas ourselves by using geometry. Not too bad. But for this next one, it gives us some irregular shapes. Don't assume those are semicircles. But instead of us having to do geometry, it just straight up tells us, hey, the area of this region is 4, the area of this region is 9, the area of this region is 2. That's great. Here's my pivot point, right? Everything is kind of in reference to this value, x equals 3. Right, because that's the point that I'm initially given. That's the point that I know. From that point to the right, it's easy. When you have negative area, remember the area is how much change your y values are going to go through. When I have this negative area, it's going to cause your graph to go down. How far does it go down? Well, however much area there is. So if I wanted to find, let's do f of 7 and f of 9 first, because those are the easier two. If I wanted to find f of 7, I could set up an equation and use your fundamental theorem of calculus. I'm just going to jump to it. I'm going to say f of 7, that would be f of 3 plus the integration from 3 to 7. And remember, the thing that you're integrating is the derivative. If you want to know something about 7, you take the value that you know, and you add the amount of change. To get the change, you integrate the rate, integrate the derivative. Remember, if that's a plus, those two should always match. So I'm setting up that equation from the fundamental theorem. Then you could rearrange it. You get f of 7 equals f of 3 plus the integration from 3 to 7. Now, f of 3, it told me, it's like 5. So think about having this like units worth of area in some imaginary bank account, right? I've got 5 units worth of area in my bank. Now, what's going to happen is I'm going to incorporate all this change. I'm going to look, what's the area bounded by f prime between 3 and 7? It's going to be this region. But that region is beneath the x-axis. So that region is going to end up counting as negative. So if I have 5 units worth of area, right? This is like my today. If I have 5 units worth of area in my little bank account, if I lose 9, that means, hey, I'm going to end up with negative 4 units worth of area, right? If you have 5 and you lose 9, you end up with negative 4. So this point here is going to be at 7, negative 4. Between 3 and 7, the change in this y value is the same thing as how much area you get incorporated by your derivative. And since this area is beneath the x-axis, your y values are going to go down, and how far it goes down is based on the area bounded by that region. Okay, but from your pivot point, from that reference point, from the left to the right, it's easy. Negative regions cause your function to go down, but here we're going to cause it to go back up because we're now going to get this positive region. Okay, so let's see, where's the function when x equals 9? You could go back and you could do back from 3 to 9, but now that we know 7, I'm going to use 7. So we'll take f of 7 plus the integration from 7 to 9. Remember, f of 7 we just did was negative 4, and then plus, let's see, I need the area bounded by f prime between 7 and 9. That would be this region right here, which is above, which counts as a positive 2. So it looks like this new point when x equals 9 is going to be at negative 2. So from this point of reference, from that point to the right, I think it makes logical sense. That's like the bank account. Like, hey, if you lost 9 units worth of area, your graph goes down 9. Or hey, if you gain back 2 units worth of area, your graph is going to go up. Right? From your pivot point or from your reference point to the right, things make sense. Positive is above, causes your graph to go up. Negative is below, causes your graph to go down. What's trickier is here, we know we have 5 units worth of area, right, when x equals 3. If you wanted to know when x equals 0, if you wanted to know how much area we had in our imaginary bank, it's like figuring out the bank account example. How much should we have before we got paid, right? So let's go through, let's do this. Let's actually set it up. I'll do a little bit more work for this one. We would integrate from 0 to 3. So integration of f prime, which would be f of 3 minus f of 0. And then this is the one that we're trying to solve for. So I would take this and I would add it over, and I would take this and I would subtract it. So f of 0 is going to be f of 3 minus the integration from 0 to 3. Okay, so I take my initial value, which was 5, and I'm going to subtract. Now the integration from 0 to 3, if you integrate from 0 to 3, right, that's left to right, that's going to end up counting as a positive 4. 5 minus 4 is 1. So there we go. It looks like when x equals 0, it looks like the y-coordinate is 1. And you're like, Mr. Bell, that's weird. Remember, we had this point at 3, 5, right? It was up at 5. That region was positive. Why did your graph go down? It's the same thing that we did in the bank account. You're trying to figure out, right, when we were looking for this y value, we were trying to figure out how much, right, if you think right here, how much did I have in my area bank account so that when I moved from that unknown amount and when I gained the 4 units worth of area, I ended at 5. Well, if you know 5 and you know you gained 4, to work your way backwards, you would subtract it, right? You would take 5 minus 4, and that tells you, oh, if I gained 4 and now I have 5, that means I must have started with 1. So whenever you're working yourself from your point of reference backwards, everything's reversed. Even though this area is above the x-axis, it's actually going to cause your graph to go down. Okay, so hopefully that makes sense. But if not, just always set up the equation with the fundamental theorem and then just isolate for the piece you're solving for and just plug it in. Just be careful though. When we're integrating from the left to the right, everything's, I think, pretty easy. Above is positive. That causes your graph to go up. Below is negative. That causes your graph to go down, right? And as I incorporate in these negative regions, your y values go down. How far does it go down? That depends on the size of the area. If I incorporate this region between 7 and 9, right, that region's above the x-axis. So when I incorporate in that positive area, it's going to cause your graph to go up. How far does it go up? The size of the area. Whenever we're working from our point of reference to the future, from left to right, I think logically that makes sense. But whenever we're working our way backwards, students typically struggle with it because you're like, oh, Mr. Bell, look, we have 4 units worth of area. So why don't we take this and why don't we go up 4? Well, think about it. If you took this value, which was 5, and if you worked your way to the left and if you added it, you'd be up at 9. Think about it. If you had 9 units worth of area in your bank account, if you then added in 4, would you end at 5? No, you would be at 13. So whenever we have these positive regions, when I'm working from right to left, when I'm working backwards, I would actually subtract the size of that area. When you're working from the left to the right, you would add it, right? You add -9 or you add the +2. But when we're working backwards, everything is reversed. This area, even though it's positive, causes your graph to go down because you're trying to figure out how much did I have so that when I gained 4, right, when I went from 0 to 3, when I gained this 4 units worth of area, I ended at 5. Well, that means your question mark must have been at 1. Okay, so just be careful. Working from, when you're integrating from right to left, the areas above the x-axis are actually going to count as negative. They're going to make your graph go down. And then areas below the x-axis, they're going to accumulate as positive because what we're doing is we're subtracting. When you subtract a positive region, it causes your graph to go down. Or if I had some negative region, if you subtract a negative area, it would actually cause your graph to go up. Hopefully that makes sense. It's kind of conceptual, but there you have it. And then let's see, if we had to sketch the graph, we know this is smooth and continuous. So do you think this is just going to be connected with sharp, straight, jagged lines? No, it's probably going to look fairly similar. Could we get a really good graph? Yes. Remember, this is the graph of f prime. We could easily tell where f is increasing. It's where the derivative is positive. We could also see where f is going to be decreasing, where the derivative is negative. Looks like we're going to have a max at 3, a minimum at 7. Looks like we're going to have points of inflection. Right, we could do all sorts of stuff, but generally you would just need to sketch it, right? And if this is a smooth curve, then typically this would also be something like a smooth curve. So something more or less like that would be a pretty decent sketch, as long as you don't connect it with like sharp turns and have pointed, non-differentiable areas at your maxes and at your mins. I think you'd be okay. But just be careful. This fundamental theorem of calculus, as we accumulate area, that's going to change the y values on your function. Whenever we work from the left to the right, I think it's easy. Positive makes it go up, negative makes it go down. But be careful. If we have to work from our point of reference backwards from right to left, everything's reversed. Think about it like the bank account. How much should I have so that when I gained 4, I ended with 5? Well, that means I must have had 1 in my bank account. I had 1, then I gained the 4, so I was at 5. Then I lost the 9, so then I was at -4. Then I gained 2, so then I was at -2. Right? This imaginary bank account, that's your y coordinate of your original function. That's another way, if you want to think about it, for doing this accumulation. A little bit tricky. Hopefully the bank account stuff, I don't know. Sometimes I feel like I do it and it just confuses students even more. But hopefully it makes sense because you guys are 17, 18 years old. You should understand money a little bit. But working your way from that reference point backwards, it's tricky. Hopefully it makes sense. Okay, let's finish these notes and then we'll be done with this video. Next example. It says, let me zoom it in a little bit now that we have done with that example. Zoom it in so the camera is not as terrible. All right, a pizza with a temperature of 95 degrees Celsius is put into a 25 degrees Celsius room when time equals 0. The pizza's temperature is decreasing at a rate given by this r sub t function, and it tells me the units for that r function are degrees Celsius per minute. And it says estimate the pizza's temperature when time equals 5. And it says, remember, or hint, the integral of the rate is your amount of change. It's like the second or the third time it's come up. That's a huge important concept. So let's go for it. If I wanted the change in temperature, right, that would be the integration of this rate function. And specifically, we know the temperature at time equals 0, and then we want to know the temperature at time equals 5. So I need to know the change between 0 and 5, which means I'm going to have to integrate from 0 to 5. And then here, we can just math 9 it, right? We're going to math 9 with our graphing data calculator. And then we could just get the value for this integral. Now, on your AP exam and also in my class, if the function is named for you, like you don't have to do this. You don't have to write it all out. Okay, 6 e to the negative 0.1 t dt. You don't have to do that. You can. But if the function is named r, you're welcome to just leave it and say, hey, I'm going to integrate r. You don't have to tell me what r is. If r is defined for you, you're welcome to just say, hey, I'm going to integrate r. But if you want to do this, that's fine. Anyways, when you integrate this, you should get something like 23.608. And the units for that, if you accumulate degrees Celsius per minute times minutes, right? The units for this would be degrees Celsius per minute. The units for time, change in time, is minutes. So the per minute and the minute would cancel, leaving me with just the change in temperature in degrees Celsius. That's your change in temperature. That's how much the temperature changes over those 5 minutes. Now be careful. You're like, Mr. Bell, why is this rate positive? Why is my pizza getting hotter after I take it out? Because the negative is in the word decreasing. Right? It says your temperature is decreasing at this rate. If it just said changing, changing is not inherently positive nor negative. Changing is just, hey, it's variable. But the word decreasing includes the negative in it. Right? So you're decreasing by this positive rate function. So my temperature, right, I would take the 95. 25 is a distractor. It has nothing to do with the question. But what I would do if it says estimate the pizza's temperature when time equals 5, I would take my initial temperature, and would I add to it or would I subtract from it? Well, the word decreasing means this rate should incorporate as negative. So I would take my initial and I would add that negative value, or I would subtract that change from it. So 95 minus your 23.608, it's going to give you 71.392. So we'll just say, hey, that pizza is going to be about 71 degrees Celsius. The integration of the rate just tells you how much change there's going to be. And then if it asks you for a final quantity, you either add to what you started with or you subtract from what you started with. And here you have to subtract it because the word decreasing kind of has the negative for you. Alrighty, so the integral of the rate is the amount to change. It's an important conceptual thing. Hopefully it's sticking in by now. Let's move on. 3 more examples and then we'll be done with this video. If f of 3 equals 5, f prime is continuous, and then it says the integration of f prime is 20. Find the value of f of 8. You're like, okay, that doesn't seem too bad. Well, here it's giving me some integration of f prime. So let's think about my fundamental theorem of calculus. I know if I integrate f prime, that would be equal to f of 8 minus f of 3. The question told me what this is, right? And the question also told me what that is. And then it wants to know, well, if I got an equation with 3 things, and I know 2 of them, I can solve it for the one that I want to know. You can do the algebra first if you would like. F of 8, just take that chunk and add it over. F of 8 would be equal to f of 3 plus the integration from 3 to 8. So if you take the value that you know and you add in the amount to change, how do you get the amount to change? You integrate the rate of change, integrate the derivative. Then just plug it in. F of 3, it told us was 5. And then that integration, it told us was 20. So if your parents ask what you did in calculus today, you say, Mom, Dad, I did 5 plus 20 today. That's the math we did on this question. Right? This is an AP exam question, and the math that you did is 5 plus 20. But you have to understand the fundamental theorem of calculus, right? If you don't know what that formula is, then you're going to miss a really easy question. You're going to miss a question where the only math you had to do was 5 plus 20. Don't miss questions like that, right? If you understand the conceptual things, right? If you know these little theorems and these little rules, a lot of the questions on the AP exam actually boil down to some pretty simple math. But you got to know the conceptual stuff first. All right, next one. Here we go. It says if the integration from -1 to 4 of 3f plus 2 equals 28, then find the integration from -1 to 4 of f. Now be careful. Do not subtract the 2 and then divide by 3. That's a trick. You're going to get it wrong. Remember, you have to recognize that this 2, it's between your integration and your differential. So that 2 isn't just a number that you can subtract. That 2 is a function that is being integrated. That 2 is a horizontal line that has area underneath it. So you need to split it up. Here, let's go. I got the 3, and then we got the integration of f, plus I've got the integration of 2. And I know I could do this. 3 integration of f plus the integration of 2. That's what would be equal to 28. So we've got 3 -1 to 4 of f plus, now let's go think about this. Remember, 2 would be a horizontal line. Well, in theory, it should be at the y value of 2. And it's between -1 and 4. So -1, 1, 2, 3, 4. So that region would end up being a rectangle. What's the height of the rectangle? 2. It's the value of the function. What's the width of the rectangle? 5. It's your b minus a. So this area, by the way, if you had to do it, right, -1 to 4 of 2, it would be 2x. And then you could plug it in. 2 times 4 minus 2 times -1. You got 8 minus -2. Okay, so the area of that rectangle, also known as 5 times 2, is 10. Right? So that integration of 2, don't just discount it, right? It's really tempting to just take the 2 and subtract it. But anything that is between your integration symbol and your differential, everything in between must be integrated. You can't just subtract it over because it's not just a number. It's a whole function that has area bounded by it. So be careful. Now that we have done the integration of 2, which is 10, now I can subtract it, right? 8 minus 10. Is 18. Divide by the 3. So I know the integration of your f of x function is just going to be 6. Okay, so be careful. A really common mistake here would be to say something like 26 over 3, where if you just take this 2 and subtract it and then divide by 2, I guarantee you if this was a multiple choice question, this would be an option, because that's a really common mistake that students are very prone to making. Don't do it. All right, last one. Here we go. We've got a piecewise function. By the way, piecewise functions, they do not have to be continuous. If you have some horizontal line, and then you have, I don't know, some other line, if you had to integrate it, you could find the area bounded by that function, and then differently, you could find the area bounded by that one. Most of the time, they're going to give you functions that are continuous, but they don't have to be. Okay, you could find the area bounded by stuff even if it's not continuous. But they do typically give you stuff that will be continuous. It doesn't have to be, but they usually will. Anyways, if I want to integrate from -1 to 4 of this function, remember, x equals 2 is your transition point. That's where you would switch from one to the next. That means I'm going to integrate this function from -1 to 2. Right? So I'd integrate this piece. So 3x minus 1 from -1 up until 2. That's where you switch over. Then I'd have to pick up where I left off from 2 to 4. And then I would be integrating the other piece, x squared plus 1. So your piecewise functions are a little bit annoying because you've got twice as much work, but typically they give you fairly easy functions. Like they're not usually hard pieces inside the piecewise. You got more work, but typically the work is easier, so it's a trade-off. They got more quantity, but the quality should be easier. Okay, let us go through and integrate. Remember, you could math 9, but we need to be able to do stuff like this because this would be a non-calculator question. All right, here we go. That would be 3/2 x squared minus x. And then I would need to evaluate that left piece from -1 to 2 plus 1/3 x cubed plus x. Then I'd have to evaluate that from 2 to 4. So I'm going to set it up. I got this left piece, which has an upper minus a lower evaluation. Plus, then we have this right integration, which has the upper minus the lower. So this is going to come from plugging 2 in. This is going to come from plugging in the -1. Let's plug in 2. So we've got 3/2, 2 squared. Let's see, 2 squared would be 4. 4 times 3 would be 12. 12 divided by 2 would be 6. And then minus 2. Now let's plug in the -1. -1 squared would be 1. So that's just going to be 3/2 and then minus -1, so plus 1. All right, and then let's plug in the 4. 4 to the 3rd power would be 64, so 64 thirds plus 4. If you plug in 2, you'll have 8 thirds plus 2. All right, now let's just try to simplify this stuff. We got 6 minus 2. Take this negative and distribute. Minus 3/2 minus 1. Then let's see, we got plus 64 thirds plus 4. Take this negative and distribute. Minus 8 thirds minus 2. Right, so lots of negatives, lots of opportunities to make a mistake. Be careful. Let's go ahead and try to see it. Look, I got a plus 4. The plus 4... and then the minus 4, those will cancel. That's lovely. So if you think about your whole numbers, you've got 6 and then a -1. So we've got 5 minus a 3/2. And then how many thirds do we have? We have a positive 64 and then a minus 8. 64 minus 8 would be 56. So plus 56 thirds. And that would be a perfectly valid answer. There are multiple other answers that could be equally right. Like if you combine those, and then you had like 8 minus the 2 minus the 1, like you could be okay. I mean, you should still get down to something fairly similar, but you could have a slightly different answer that's mathematically equivalent. All right, if you want to combine it to all one fraction, right, and get it to one singular answer, which you would need to do for a multiple choice. Free response, right? For a free response, that's a perfectly good stopping spot, right? That is safe to stop at. But if it was multiple choice, you'd have to go farther. So the common denominator that you would need is 6, because that's the least common multiple between 1, 2, and 3. So let's see. This would end up being, if you make it, that would be 30 over 6. If you multiply this by 3 to get your common denominator, you have to multiply that by 3, so that'd be 9/6. And then if you multiply that by 2 to get your common denominator, you'd have to multiply this by 2. So look, it's going to be a 1/12. So let's see. That would be 142. And then 142 minus 9 should be 133/6. Right, so those two answers are the same. What I always like to do is just check it, right? Let's plug it into the calculator. So I've got 5, get out of there, 5 minus 3/2 plus 56 over 3. This gives you this weird decimal. You can hit math, enter, enter, and it'll change it back into the fraction, and it'll give you the simplest version of the fraction. So that's really nice. Even if you had something like 266 over 12, you're like, okay, math, enter, enter. It'll turn it into the simplest version of your fraction. All right, so your fundamental theorem of calculus, remember there's lots of applications for it. The area bounded by your derivative. That's how much change your y values are going to go through. If your area If your area is above the x-axis, right, that's gonna be a positive accumulation. But if I'm working my way from this reference point backwards, you'd actually subtract that positive. Or if I'm working from my point of reference to the future, right, negative makes the graph go down, and then the positive area would make it go up. How far it goes down or how far it goes up to get from one y value to the next, that's dependent on the size of the area. But integrating from the left to the right, going from your point of reference forward, those are pretty easy. Working your way backwards is a little bit harder. Think about it like the bank account example, and then hopefully it'll help.